In the previous video, we got familiar with TensorFlow graphs, ops, variables, and constants. We also saw how TensorFlow computes gradients of arbitrary functions. In this video, we will apply the machinery to estimate a linear regression model in TensorFlow. We will do it using two methods. The first one is based on a normal equation for linear regression that we introduced earlier. The second one is a probabilistic method called the maximum likelihood estimation, or MLE for short. So let's just dive in and see how it all works.
Here we are in a notebook. The first cell are usual imports. We will also import TensorFlow STF. The second cell is the graph reset utility function that we already used in our previous notebook. The third cell defines a linear regression model that we fit. We have three predictors x1 to x3 that are all uniformly sampled on the interval of -1 to 1. Then we weight them with weights b1 to b3, add to this an intercept a, and finally add a Gaussian noise with volatility sigma equals 10%. Next, we simulate 5,000 points of such synthetic data and then split it in ratio of 4 to 1 into the train and test data sets. Let's check what we get here. Okay, now our data is ready and we can move on with estimations of the model. The first calculation shows you how this can be done in plain NumPy. We define an augmented data matrix by adding a column of ones at the left here and then apply the normal equation here. Okay, so here's the result. So far so good. So let's do the same thing in sklearn now. Instead of explicitly coding up the normal equation here, now we can simply call the fit method of the linear regression class in sklearn. Let's run it, and here's the result. As you see, it's identical to the result we got in NumPy, and this is because scikit-learn uses NumPy under the hood. Now let's see how the same can be done with TensorFlow. Here we first again make an augmented data matrix that we will call X and P. And then we create two TensorFlow nodes X and Y, which will be TensorFlow constants that will be initialized to X sub and P and Y train at runtime. Then we implement the normal equation in TensorFlow, this time using TensorFlow matrix operations. Then we run our session to compute the values of theta. And here are the results. Now let's make a TensorFlow class for linear regression that implements both the normal equation and another method called maximum likelihood estimation, or MLE for short. If you're not familiar with the MLE, don't worry, we will cover it later this week, so you will be able to return to this demo if you don't understand the formulas that I will be implementing in TensorFlow for the MLE method. Okay, so what do we have in this class? Let's look at the class constructor. The first thing that needs an explanation here are these two attributes, self-x and self-y. They are declared as placeholders. Placeholders are special nodes in a TensorFlow graph that do not do any computation but simply pass the input data at runtime. At the stage of creating a graph, TensorFlow needs to know what type of a tensor it should create for this data. So the first argument of it is will be a type of this data, and the second argument will be the shape of a tensor representing this data. Here the shape of a tensor to fill the placeholder node self.x is shown as none and n features. This means that the second dimension, that is the number of columns in a data sample, will be n features, But the first dimension, the number of points in a data sample, can be anything. The next two lines implement the normal equation as we just saw above, and the mean square error. Let's move to the second method implemented in this class. With the MLE method, we estimate all parameters of regression plus the noise variance. This makes n features plus 2 parameters to estimate. Therefore, we create a variable self.weights that will store the result of our MLE estimation. The next few lines compute the negative log likelihood function for linear regression. Please pay attention to a little trick I used here to define the standard deviation or volatility sigma as a square of the last weight plus some small positive number. This is made to ensure that the log likelihood defined here stays well defined for all values of weights. Finally, the last line in the constructor defines a node that specifies an optimization method that will be performed iteratively. TensorFlow has a number of built-in optimizers, and we will use the one called the Atom optimizer. Another choice could be a gradient descent optimization, which is commented out here. We will talk later about how these algorithms work in theory, but now we are looking at how they work in practice for this simple example. The rest of the class is a function that generates the synthetic data, which I copied here inside the class from the above cell for convenience. Now, the main function here creates the data first, and then creates the train and test data sets. Then it creates our linear regression model here and starts the TensorFlow session. Now, please pay attention here to how we run the graph. To compute nodes defined in our class, we need to fill the placeholders that we created there. And this is done at runtime using this dictionary called feed_dict, whose keys are placeholders nodes and the values are model inputs. Such calculation is done to compute both the optimal values of parameters and the train and the test errors. Please note that in the last two calculations, we compute the same node but fill the placeholders differently each time with different data. This is for the normal equation implementation within the class. The next lines show the training for the MLE method. Here we run 1000 steps of optimization that will keep updating model weights according to the minimization scheme that we defined in the class. This call returns both the current value of the loss and updated model weights. And after the training is done here, we test the model. After that, we compute the model predictions for the noise volatility and print the results, as well as show a three-dimensional projection of our prediction results. Let's execute this cell and execute the next one to see the results. And here are the results. As you can see, both methods produce very similar results and both provide a good fit to the data. This notebook contains below one more implementation of linear regression, this time using a different algorithm called stochastic gradient descent and implementing linear regression as a single neural network. All these will be topics for our next videos. You can come back to this notebook later to see how they can be implemented after you get familiar with these topics. For now, let me stop with this notebook at this point.
Okay, now after we saw the working of linear regression in TensorFlow and used both normal equation solution and the maximum likelihood solution, we are ready to move on with regression problems in machine learning. In the next video, we will look at how regression problems are solved using neural networks.